for today. We're continuing on in chapter 19, which focuses a lot on carbonyl addition chemistry. So for exam 2, the exam 2 chapter content is outlined in the syllabus. I believe it's going to cover from 17 to 20. So we have about 1.5 more chapters before we're ready for another exam. So in chapter 19, we're focusing extensively on carbonyl addition chemistry, such as 1,2 addition. So last class session, we looked at the formation of hemiacetals and hemiketols. So in this case, acetal formation and hemiacetal formation occurs readily under acid catalyzed conditions. When we're working under acid catalyzed conditions, a critical feature that we highlighted last class session is that because we have a weak nucleophile, we typically activate our nucleophile via protonation. So we activate our carbonyl via protonation. We now can attack our carbonyl with weaker nucleophiles, and then from there, we have a proton transfer to generate our first adduct. This adduct, where we have addition of a single molecule of alcohol into a ketone, is known as a hemiacetal. Further protonation activates water as a leaving group, which then leaves to make this highly activated electrophile, which can be readily attacked by another equivalent of alcohol. From there, a second proton transfer step gives us an acetal. Acetals are isolable species, though they're typically unstable to acidic conditions. Use of cyclic acetals, such as the structure shown here, discussed previously last class session, these kinds of cyclic acetals are substantially more stable. And the reason for that is you have this tethering effect where your two equivalents of alcohol are connected. That makes it much harder for you to dissociate and break both of these carbon-oxygen bonds via hydrolysis. So does that recap make sense to everyone? Does that recap look familiar to everyone? This typical mechanistic pattern of carbonyl addition under acidic conditions. How does everyone feel about that? Do we have any questions? Okay. So we talked a lot about acetal formation, and we showed last class session the mechanism for acetal and hemiacetal hydrolysis. So now let's showcase and let's practice drawing the mechanism for this reaction. So we have the following structure and we're treating it with acid. What do we call this structure? What do we call this structural motif? Where we have two almost ether-like functionalities bonded to a single carbon. What do we call this functionality? We just saw it on the previous page. What do we call this functionality? An acetal, exactly right. So if we're hydrolyzing an acetal, we're clearly going to have a hemiacetal intermediate, and then our product is going to be some sort of ketone or aldehyde. In this case, this structure has a slightly different name. Rather than acetal, oh yeah, actually acetal is perfectly fine for this case. Yeah, so acetal and hemiacetal is perfectly reasonable. And then the product we get, rather than a ketone in this case, we get an aldehyde. Okay, so now that we have a rough sense of what's going to happen, let's try to draw out a full arrow pushing mechanism. So we have plenty of space on the class whiteboard. So I'd like us to take a moment and to try to draw out or describe the steps for this mechanism and to talk a little bit about what will the intermediate look like and what will the final product look like from this reaction. So I'd like students to share their proposed responses as either pictures of their written work in the chat. You can also describe the mechanistic steps in the chat or verbally, or you can annotate your responses directly onto the class whiteboard. So I'd like us to take about 3 to 4 minutes, and I'd like to see some student responses for the following example. And one thing to think about, we're under acidic conditions. So what's the first thing that's going to happen if we have these basic lone pairs? And don't be shy to voice your proposed responses in the chat or verbally, or annotate your responses directly onto the class whiteboard. And I'd be happy to provide input and feedback. So, does anyone have a proposal for the first step? We have an acetal, we're treating it with aqueous acidic conditions. So what's the first thing that's going to happen when we have these basic lone pairs? What do we think? So we know we're probably going to get a hemiacetal and then finally an aldehyde. So the first step in this process is we need to activate one of these ethers as a more effective leaving group. So as one of your classmates has very astutely pointed out, we have strong acid present in solution. We have a basic lone pair. So we're going to protonate one of our ethers. Okay, perfect. So now that we've protonated one of our ethers, we now have a very interesting situation. Let me draw this a little more accurately. There we go. Okay, so we now have this protonated ether. And now looking at this protonated ether, or we can think of it almost like a protonated alcohol, does that look like a good leaving group, a bad leaving group? In the past, we protonated water, right? We protonate alcohols, we get water, or we even protonate water to get H3O pluses. And in general, protonation activates leaving groups. We get a much more activated leaving group. So this protonated alcohol looks like quite a reasonable leaving group. It's almost like water is a good leaving group in a way. So then, if we have a good leaving group, can we kick out this leaving group? Can we kick out this leaving group? Would anyone like to draw the arrows to show the loss of this leaving group? How would we lose an equivalent of alcohol? Would anyone like to try annotating using the annotate tool? So we have this great leaving group. How would we lose this leaving group? Would anyone like to share a photo of their mechanism? Would anyone like to try talking us through the next step for this mechanism, or sharing in the chat the next step for this mechanism? Or does anyone have a question that they'd like addressed to help us advance this discussion? So we've protonated one of our ethers. We have a much better leaving group. So now, as your classmates are drawing out, we can kick out an equivalent of alcohol. Exactly right. Perfect. So from here, that gives us the following pretty activated cationic species. Okay, so now if you look at the following species, this reminds me a lot of a protonated carbonyl, right? It's an activated, pretty electrophilic carbonyl functionality. And if we have water floating around, we have a lot of water, we're under aqueous acidic conditions. What's going to happen next? Under aqueous acidic conditions, we have this intermediate. We've kicked out an equivalent of alcohol. We now have this pretty electrophilic carbonyl-like functionality. So what is water going to do? Water being a tolerable nucleophile under these conditions. Would anyone like to draw the arrow pushing for this next step? We are hydrolyzing. We are, in effect, displacing the alcohol equivalents with water via 1,2 addition and elimination. So would anyone like to show this next step where we have this activated electrophile, we have nucleophilic water? What will we see happen? We have an electrophile, we have a nucleophile. How will water react? And you can share your responses in the chat or verbally. And don't be shy to flip through the earlier pages of your notes or to ask a question. We're doing this recap together, and I'm sort of fielding ideas from the class to help us both review this mechanism, and so that way if we have any questions as we work through this problem, we can get those questions addressed. So, do we have any proposed mechanisms for this next step? We have an electrophilic species and we have water. So what will happen from there?
Will it attack the double bond?
Yep, and will it attack at carbon or oxygen?
Oh, sorry, the carbon?
Yep, exactly right. Carbonyls and carbonyl-like functionalities are electrophilic at carbon. So we have addition of an equivalent of water. Now, when water adds, we end up with this pretty good leaving group. And rather than just kicking out water and going in reverse, since this entire process is in equilibrium, we now have something that closely resembles a hemiacetal or hemiketal. So in order to get an isolable, quote unquote, isolable hemiacetal, what do we need to do as a cleanup step? So a hemiacetal, we have one equivalent alcohol, one equivalent of water, but this species is protonated right now. So if we wanted to draw out a nice, clean hemiacetal structure, what do we have to do if we want an isolable neutral species? Yep, use water to remove the proton. Yep, this is just a nice, simple cleanup step where water pulls off a proton, and now we have a isolable, though not particularly stable, hemiacetal. Okay, so now, this is where things get a little bit interesting. We're still under acidic conditions. So the next step to go from a hemiacetal to the aldehyde follows the same general mechanistic pattern, right? Protonation. You activate your leaving group, you kick your leaving group out, and then from there you have your carbonyl equivalent. So following that general pattern of protonation, loss of a leaving group, what do we think is going to happen if we want to get rid of a second equivalent of alcohol? So we have these basic lone pairs. We're still under acidic conditions. So what will happen? following this pattern of protonation, loss of a leaving group, what do we think is going to happen next? So we have our hemiacetal. We're still under acidic conditions. We know that hemiacetals under aqueous acidic conditions will decompose to yield an aldehyde. Now my question to everyone is, how do we go about getting that aldehyde? What's the next step? We're under acidic conditions. We have this ether. We have this alcohol functionality. So what's our next step?
We do a proton transfer.
Yep. Okay. And what are we going to protonate? Oxygen A or B?
It's oxygen B.
We can protonate oxygen B, but that would get us right back to this intermediate. So that does happen. It is an equilibrium, but it would give us just our starting material. If we wanted to kick out this ether functionality or kick out this alcohol equivalent, what oxygen would we need to protonate, A or B?
So then it would be oxygen A.
Yep, exactly right. And in that case, that would give us a productive pathway where we can lose and activate this alcohol equivalent as a leaving group. And we can see that because now, after protonation, we have a much more activated leaving group, right? Generally, protonated species are better leaving groups. So from there, how are we going to kick out this leaving group? Do we have a lone pair available? Can we form a carbonyl by kicking out this leaving group? Can we perform a 1-2 elimination reaction?
Yes.
Yep. Would anyone like to draw the arrows for that? Or would you like to explain verbally what lone pair am I kicking down to lose this leaving group? Oh, perfect, perfect. Yep, exactly right. The lone pair on the alcohol oxygen gets kicked down and we lose our leaving group. Would you be able to draw that second arrow for the loss of the leaving group? Perfect, perfect, exactly right. So let's redraw that now. So we kick out our leaving group. We now have a protonated aldehyde. So as our final step, and this is the last step that we need before we get our final product, we have a protonated aldehyde. We typically don't isolate protonated species. So what is our final step to get an isolable neutral product?
Deprotonate the oxygen.
Yep, exactly right. So water will pull off this proton and we get a cleanly isolable aldehyde. Does this mechanism make sense?
So we're pretty much always going to be making like a hemiacetal when it comes to these reactions.
Yes, so typically when you're making an acetal or when you're hydrolyzing an acetal, you always end up going through a hemiacetal intermediate. Yes, that is correct. Any other questions on this example? Okay, so let's now talk about another variant of these carbonyl addition reactions, which involves nucleophilic addition of hydrogen cyanide to make what's known as a cyanohydrin. So aldehydes and unhindered ketones react reversibly with hydrogen cyanide to yield cyanohydrins. So to give you a sense of what a cyanohydrin looks like, we have an sp3 hybridized carbon atom containing an alcohol and a nitrile functionality. Now, addition of hydrogen cyanide under acidic conditions is slow. However, base catalyzed conditions generate the nucleophilic cyanide ion that reacts readily. Nucleophilic addition of cyanide to carbonyls yields a tetrahedral intermediate, which is then protonated. Now, one thing that's very unique about cyanohydrin formation is that the equilibrium favors the adduct. This isn't like a typical nucleophilic addition into a carbonyl, in that this tetrahedral product, this tetrahedral adduct, is favored, and you can isolate these cyanohydrins. So the mechanism involves attack of your cyanide onto your electrophilic carbonyl carbon. We kick up our lone pair, and that generates this tetrahedral intermediate. This alkoxide ion can be protonated either with acid or an extra acid generated as a byproduct in this reaction, or with an added equivalent of acid during the quench step. Note, just like any alkoxide ion that you get from like a Grignard addition or from a reduction, you can trap this alkoxide ion with electrophiles. And that's going to be quite useful. So, any questions on the mechanism for cyanohydrin formation? As we've seen, it's often best run under basic conditions. Under acidic conditions, it's quite a slow reaction, and it's not particularly fun to work with hydrogen cyanide. Any questions on this idea? Okay, perfect. So, cyanohydrins aren't just useful as end products. They can also be derivatized, as we'll talk about in later chapters. The nitrile group can be reduced with lithium aluminum hydride to yield a primary amine. The nitrile group can also be hydrolyzed using hot acid to yield a carboxylic acid. This is a very useful conversion of an aldehyde or ketone into a different functional group. Additionally, I'd like you to note that we have in effect added a carbon to our carbon chain. So this is a useful addition to our toolbox in terms of adding one carbon fragments. Does this idea make sense to everyone? Perfect. So let's keep going now. And in this case, I'd like us to predict the product from each step of the reaction sequence and draw a mechanism for the following reactions. And what I'd like to focus on just for right now is the mechanism for this first step that I'll label A. For the second step in the sequence, I'd like you just to predict the product, and we'll draw out the mechanism together as a class for the second step. So let's take about 3 to 4 minutes, and let's try to predict the product from these 2 reaction steps. And then I'd like to see a mechanism for the first step, which I've labeled as A. And if there are any questions I can address, don't be shy to let me know. Any questions that I can address? And if there are any questions I can address, don't be shy to send them my way or ask them in the chat or verbally.
So would we maybe kick the electrons from the double bond up to the oxygen to protonate it, or so that we can eventually protonate it?
Sure, that would be drawing like a resonance form. But we have hydrogen cyanide, which is a reasonably competent acid, right? So if we draw the structure for hydrogen cyanide, you were alluding to protonating this aldehyde, right?
Yes.
And so how would we draw that in an arrow pushing way? So we have a basic lone pair, we have an acid. So how would we draw that acid-base reaction?
Well, don't we have to get rid of the proton on the cyanide first? Or no?
Not necessarily. We'll make our nucleophilic species during this acid-base reaction. But if we wanted to just, we have this aldehyde, we're under acidic conditions, and we're activating this aldehyde via protonation, how would we draw that? How would we draw that protonation step?
So the cyanide would attack the carbon.
That's the next step, yes. But in terms of activating, we'd first just protonate our carbonyl oxygen with our acidic equivalent of hydrogen cyanide. However, you are alluding to a very important point. Once we protonated our aldehyde, once we have this very activated electrophilic species, in terms of our next step, we now have this nucleophilic equivalent of cyanide floating around, and where will cyanide prefer to attack? So we have this electrophilic species, we have a nucleophilic equivalent of cyanide that we've generated. So now what would happen? Perfect, yep. Your nucleophilic equivalent of cyanide will attack your electrophilic carbonyl carbon, and we break the carbon-oxygen double bond to make a single bond. Perfect. So let's just re-annotate that. So cyanide will attack the electrophilic carbonyl carbon. We will break the carbon-oxygen double bond, and we get our first isolable species, which is our cyanohydrin. Now, my question to everyone is, when we treat this cyanohydrin with lithium aluminum hydride and then quench with water, these are two separate steps. First, lithium aluminum hydride, probably in ether or THF, then water. What product will we isolate? So I'd like us to take a few moments and let's try to predict the structure of the product. And then we'll talk about the mechanism for this second step together as a class. So does anyone have a proposal for the structure of our product? So lithium aluminum hydride is a pretty strong reducing agent. And what functionality can be reduced in this molecule, in this cyanohydrin? So when we have someone drawing out the structure. So this nitrile is pretty reactive to hydrolysis, reduction, and even nucleophilic addition, such as that with Grignards, though you'd have to protect the alcohol first. Anyway, so when we treat this nitrile with lithium aluminum hydride, we would reduce the nitrile all the way down to the primary amine. Yep. And the student proposed structure looks completely reasonable. So let's clear that annotation. Let's just show the structure of the product. And it's good to see that you noted the fact that when the nitrile is reduced, we still have this methylene group present. So let's talk about this mechanism, and this is just sort of a brief teaser of the next chapter, which is chapter 20. So we have our nitrile. And the interesting thing about nitriles is you can think of them very similar to carbonyls and imines in terms of which site is reactive. The nitrile carbon is relatively electrophilic and as such can be attacked with common nucleophiles. So if you have a hydride equivalent, that hydride equivalent can attack your nitrile carbon and generate an imine. Now, am I forgetting a hydrogen? Where? Which, would you be able to circle it? Oh, you mean explicitly drawing out this hydrogen here? Yeah, the hydrogen's implied, but I can show that. For here, this carbon, it has 4 bonds to it. So yeah, the hydrogen has been accounted for. But that's a good question to ask. I drew out the hydrogen in this case really to highlight this cyanohydrin came from an aldehyde, just to help us get a sense of how the carbons are connected. Okay, now for this substrate in particular, you can draw a proton transfer just because you have this reasonably acidic alcohol, you have this basic almost iminium anion, so you can just as easily pull off this proton. It's a 5-membered ring, so it's reasonably geometrically allowed. And then from here, we still have this imine. It's still electrophilic, so a second equivalent of hydride can just as easily attack your generated imine. And from there, we can generate an ammonium ion. Now, of course, we're not able to isolate this highly basic dianion. So that's what the next step is for. So we have this intermediate floating around in solution. And when we treat with water or a source of aqueous acid in our quench step, we will easily be able to protonate our basic ammonium and alkoxide anions and generate our neutral product. So during the quench step, we protonate both the ammonium and alkoxide ions, and that gives us our isolable primary amine product. Does this mechanism make sense to everyone? It's very similar to the mechanism for example, exhaustive reduction of an ester. You have addition of 2 equivalents of hydride, and then you protonate your generated alkoxide and ammonium intermediate. So forming this alkoxide is unique for this substrate. You can draw an intermediate with a -2 formal charge on nitrogen. However, that only really occurs if you don't have any other acidic functional groups in your molecule, or if you have a completely aprotic solvent, because that essentially that dianion is not particularly stable. It's quite basic. That is commonly drawn for the mechanism for nitrile reduction, but for this particular substrate, I showed the proton transfer. And that's just appreciating the fact that alcohols are acidic. Any other questions on this example? Does this mechanism for nitrile reduction make sense? Perfect. Okay, so let's look at the next sort of use of these cyanohydrins, which are to prepare carboxylic acids. So I'd like us to predict the product from each step of this reaction sequence and to draw a mechanism for the following reaction. And so I'd like to see students predicting the product and drawing the mechanism for step A. And if you'd like, I'd like some students to attempt to begin to draw the steps for step B. So let's take about 3 to 4 minutes and let's try to predict the product from each step, as well as to draw a mechanism for each step in this reaction sequence. So we're treating an aldehyde with an equivalent of hydrogen cyanide. So we're under acidic conditions. So first step, we're going to protonate our carbonyl. From there, we have this activated protonated aldehyde, which can be readily attacked by a nucleophilic cyanide. Next, our equivalent of cyanide, which is our nucleophile, will attack our electrophilic carbonyl carbon, generating a cyanohydrin. Perfect. So we make the following cyanohydrin after our first step, which is treatment of this aldehyde with hydrogen cyanide. Now, if we treat this cyanohydrin with aqueous acid, what will happen next? Now, to help us have a clear starting point here, I'm just going to redraw the mechanism and product for this first step, just so that way we have a common reference point before moving on to the next mechanism. So we're going to protonate our aldehyde. We now have an activated electrophile, which can react with nucleophiles such as cyanide. Our nucleophilic equivalent of cyanide will attack our electrophilic carbonyl carbon. And then from here, we will get a cyanohydrin. Okay, now that we have our cyanohydrin, I'll redraw that structure down here. Would anyone like to give an attempt to draw the mechanism for hydrolyzing this cyanohydrin? So let's take about 3 to 4 minutes and let's first think, when we treat this cyanohydrin with aqueous acid, what functional group will we get out? And would anyone like to try to volunteer drawing a mechanism for this second step? So we have students noting that if you treat this cyanohydrin with aqueous acid, we will hydrolyze our nitrile and we end up being able to isolate a carboxylic acid. Yep. So would anyone like to try to draw the mechanism for this process? How are we going to get this carboxylic acid from a nitrile under aqueous acidic conditions? Would anyone like to propose a mechanism or series of steps? Or does anyone have a question as they work through these mechanisms? So to give everyone a preview of the next chapter and to talk a little bit about the mechanism and to help us notice some general features. Oh, so we have a student starting to draw out their proposed steps. So we have H3O plus, we're under aqueous acidic conditions.
I believe we would just go like here.
Yep, that's one of the steps. But in order to activate our nitrile, just like activating our carbonyl, what's one way we can activate a carbonyl, nitrile, or imine? What's one way that we can activate those functional groups for a reaction? Via protonation, as many of our classmates are alluding to. So let's put these student proposed steps together. So we have a proposal that we're going to protonate our nitrile. And then we have a second proposal that after protonation, as one of our steps, an equivalent of water is going to attack our nitrile. Okay, so we protonated our nitrile. From here, water can attack. And we now have this intermediate that begins to remind me a little bit of almost like a hemiacetal in a way. Not quite, but you can get the fact that they look somewhat similar. Okay, so from here, we now have this adduct. And in the end, we're going to need to kick out an equivalent of ammonia as a leaving group, right? So in order to facilitate that, how do we activate this equivalent of ammonia? Yep, we're going to have a proton transfer, but we're going to draw it as inter rather than intramolecular because it's not quite geometrically set up. 4 atoms apart, that's a pretty small cyclic transition state if you're going to have a proton transfer. Okay, so we have a proton transfer. We've now heavily activated this imine-like intermediate. We now have a pretty electrophilic carbon. So what's our next step? We still have water floating around, and we have this pretty electrophilic imine carbon. So what's going to happen next? So we have an electrophilic carbon and a nucleophilic equivalent of water. So we have a nucleophile and we have an electrophile. So what would happen next? Yep, nucleophilic attack of water on our electrophilic carbon. Okay, we're almost done with this mechanism actually. It's very reminiscent almost of carbonyl substitution mechanisms that we've seen, and also the mechanism for example, acetal hydrolysis. Okay, so we now have our amine and we have water added. So how do we activate our amine as a leaving group? How do we activate this amine as a leaving group? So just like before, how did we go about activating our amine as a leaving group? Another proton transfer, exactly right. So H3O plus transfers a proton, water removes a proton, and now we've prepped this molecule for the final last step. We have this reasonably good ammonium leaving group, and now we're ready for the last step, or at least the second to last step. So what's going to happen next? So we have a great leaving group in place. So can we regenerate a carbonyl? Can we form a relatively stable carbon-oxygen double bond? Yep, we're gonna kick down a lone pair from one of our oxygens and we'll lose our leaving group. That in turn gives us a highly acidic protonated carboxylic acid. And for our final cleanup step, we generally don't isolate cationic species. We generally isolate neutral species. What's the last step in this mechanism? What's our last cleanup step if we want to isolate a neutral product? Deprotonate with water, exactly right. And that in turn gives us our final isolable carboxylic acid derivative. So although this mechanism is steppy, sure, if you break down each of the steps, it reminds us very much of many other typical carbonyl addition mechanisms and the mechanisms that we discussed in terms of acetal hydrolysis. Does this mechanism make sense to everyone for nitrile hydrolysis to give a carboxylic acid? Any questions on this example and the mechanisms that we covered together? Perfect, perfect. Okay, so one thing to note, and one thing I'd really like us to appreciate, is that when you make a cyanohydrin under basic conditions, the alkoxide ion that you generate can be trapped with electrophiles. So you can even, for example, protect the cyanohydrin alcohol with trimethyl silyl chloride. Just as a refresher, TMS or trimethyl silyl chloride looks something like this. In fact, there are even reagents that are used specifically for protected cyanohydrin formation, such as, for example, TMS cyanide, which both facilitates the nucleophilic addition and protects your alcohol. So, with this idea in mind, let's showcase the mechanism for this two-step sequence that's run in the same reaction vessel, and I'd like us to draw the mechanism for each step. So this time we're using sodium cyanide, so we're working under basic conditions. And the reason why that's important is because the mechanism changes slightly compared to under acidic conditions. So would anyone like to try to annotate the mechanism for each of these two steps in the reaction sequence? So let's take a few minutes as we work through this example, and I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. So when we treat an aldehyde with sodium cyanide, what is going to happen? So as a student noted, sodium cyanide is a nucleophile. The aldehyde carbon is electrophilic. So cyanide will attack the electrophilic carbonyl carbon, and then we break our carbon-oxygen double bond. Okay, so from here, we don't get a cyanohydrin just yet. So we get the following alkoxide ion, and if we treat this alkoxide ion with TMS cyanide or trimethylsilyl, sorry, not TMS cyanide, trimethylsilyl chloride or TMS chloride, when we have this alkoxide ion present, what will happen? We have a nucleophile, we have an electrophilic protecting group reagent. So TMS chloride is electrophilic. So your alkoxide will attack the electrophilic silicon atom, and we'd end up with a TMS protected alcohol. This is very useful from a synthetic perspective because it now allows us to actually use Grignards. It allows us to further manipulate this nitrile without having an alcohol getting in the way. Further, and this is important, these protected cyanohydrins, these kinds of protected cyanohydrins, you'll see a lot in later chapters because they're a useful method for generating very unique anionic species. This proton here can actually be removed under certain conditions, and it allows us to generate a very useful nucleophile. We'll talk more about that in later chapters. The main thing I want us to take away from this first section is that we can make cyanohydrin derivatives in the same reaction vessel. Does this idea make sense to everyone? Perfect. Okay, so what we're now going to do is we're going to review nucleophilic addition of Grignard reagents and Hydride reagents. So treatment of aldehydes or ketones with Grignard reagents yields an alcohol. Grignard reagents can be thought of as carbon anion equivalents, and they add readily and attack the electrophilic carbonyl carbon readily. From this tetrahedral intermediate, which is functionally an alkoxide anion, we can either protonate the alkoxide ion to get an alcohol or trap the alkoxide ion to make any number of ether or protected derivatives. Okay, we've seen this mechanism time and time again. Let's now discuss the addition of hydride reagents into carbonyls to generate alcohols. Lithium aluminum hydride and sodium borohydride react as hydride donors. This reaction is functionally irreversible because you're never going to be able to kick out hydride as a leaving group. Generally, carbon anions and hydride are terrible leaving groups. We'll see a few exceptions, but in most cases, you're never going to kick out an alkyl group or hydride as a leaving group. Hydride reagents are useful because they allow us to make primary and secondary alcohols. As you notice, people prefer to use sodium borohydride rather than lithium aluminum hydride because sodium borohydride is a little bit more selective. In terms of the mechanism, hydride, which is a nucleophile, attacks our electrophilic carbonyl carbon. We break our carbon-oxygen double bond. That gives us an alkoxide ion, which is then protonated during the quench. If you use a Grignard reagent, we get a secondary and tertiary alcohol. Generally, you don't see appreciable stereocontrol, and the rules for predicting the stereochemical outcome of these additions are saved for upper division organic courses. So, any questions on hydride and Grignard addition into carbonyls?
Can you show the mechanism for these hydride to alcohol?
For the
aldehyde, and then the hydride reagents give secondary alcohol?
So if you have an aldehyde, you'll always get a primary alcohol. There's no, because the substitution of the alcohol depends on whether you start with an aldehyde or a ketone. So for example, if you have an aldehyde, hydride attacks and you get a primary alcohol. If you have a ketone, when hydride attacks the carbonyl carbon, you get a secondary alcohol. The substitution is based on the number of alkyl groups attached to your carbonyl initially. Does that make sense?
Yeah, okay, thank you.
Perfect, perfect. Any other questions on Grignard addition and hydride addition into aldehydes and ketones? Perfect. So, just to make sure that we're comfortable with this mechanism, I'd like us to predict the product from each step of the reaction sequence and draw a mechanism for the following reactions. Just for your note, just to refresh everyone, when a structure is drawn in brackets, it's generally not isolable. It's like an intermediate. This methodology is commonly used to convey the first step makes an intermediate, and we treat that intermediate with further reagents to get an isolable product. So this is an example of Grignard addition into a carbonyl followed by trapping with an electrophile. So let's take a few moments and let's try to predict the product from this reaction and to draw a mechanism for this reaction. So let's take about 3 to 4 minutes and let's try to draw out a mechanism for this reaction. And don't be shy to share your proposed mechanisms in the chat, verbally, or annotated directly onto the class whiteboard. So we have our Grignard, which is ethyl magnesium bromide, which is a wonderful nucleophile. We have an electrophilic carbonyl carbon, so our Grignard will attack and add into our carbonyl, and that makes an alkoxide ion. Now, alkoxide ions are bases, that's true, but they're also pretty wonderful nucleophiles. So if we have this alkoxide ion sitting around in solution, we can actually trap that ion with an electrophile. And that's what this second step is for. We have this alkoxide ion floating around. We treat it with 2-chloropropane. And what happens next? So we have our nucleophilic alkoxide ion. We have an electrophilic alkyl halide. So if we have a nucleophile and an electrophile, we'll see an SN2 reaction. Would anyone like to draw that second step? Yep, so you have your alkyl halide. Our nucleophile attacks the electrophilic alkyl halide carbon via an SN2 reaction. And that in turn gives us our substituted ether product. What's the name for this reaction, by the way, where you have an alkoxide ion and an alkyl halide? What do we call that reaction? It's a named reaction, one of the few that we actually cover extensively in this course. This is known as the textbook Williamson ether synthesis. That's part of why I included this follow-up example and why I chose this example as review, because it encapsulates this idea of Grignard addition into carbonyls and it reviews the Williamson ether synthesis. And the beautiful thing about this process, and this is pretty nice, is that because the alkyl halide is our trapping agent, we can use an excess of it. And even if we get a pretty abysmal yield, that doesn't entirely phase us as much because we're using an excess of the alkyl halide. So it allows us to use relatively unreactive alkyl halides. I mean, you won't be able to get away with like a tertiary alkyl halide or anything of that sort, but it does allow you to use relatively unreactive alkyl halides just because you're using such a large excess. So, does this mechanism and does this reaction sequence make sense to everyone?
So what would go inside the brackets there, Professor?
The intermediate in the brackets would be the alkoxide ion generated from the first step.
Oh, okay, I see.
Any other questions? Okay, so let's look at one other example where we can apply this idea of Grignard addition into aldehydes and ketones, followed by both Williamson ether synthesis reactions and also acylation reactions. So in this case, we're looking at Grignard addition into an aldehyde, and this time we're trapping the aldehyde with we're trapping our alkoxide ion generated from the aldehyde with an acyl chloride. So let's work on this example for about 3 to 4 minutes. Let's try to get a proposed mechanism shared in the chat verbally or annotated on the class whiteboard. And I'd like to see products predicted from step 1 and step 2 of this 2-step sequence. So, as the students have correctly noted, we have an electrophilic carbonyl carbon. We have a nucleophilic Grignard reagent. So our Grignard reagent will add in to our electrophilic carbonyl carbon. From here, we have this alkoxide ion, which is a pretty competent nucleophile. So if we trap this alkoxide ion with an acyl chloride, would anyone like to show the second step for this mechanism? And I'd like you to remember, we've seen similar examples of this in the acylation reactions of alcohols. So, would anyone like to propose a mechanism for this second step? We have a nucleophilic alkoxide ion. We have an electrophilic acyl chloride carbon. Our nucleophile will attack the acyl chloride. We get this tetrahedral intermediate. And once we have this tetrahedral intermediate, it's going to collapse to regenerate our carbonyl by kicking out the best leaving group. Now, of course, we can kick out the alkoxide ion, but that's non-productive. Eventually, we'd end up kicking out the chloride and generating our acylated alcohol. Yep, and the student proposed mechanism looks completely reasonable. Oh, perfect. So what I'm going to do is I'm going to re-annotate the student responses, but the student responses proposed were perfectly correct. So ethyl magnesium bromide, no worries. So ethyl magnesium bromide attacks the electrophilic carbonyl carbon. That in turn generates an alkoxide ion. And then from there, it's going to attack the electrophilic acyl chloride carbon. And we get a tetrahedral intermediate. Now, this tetrahedral intermediate will collapse and we'd kick out our best leaving group, which is chloride. And that in turn gives us our isolable final product. So this is a wonderful method to generate a lot of structural diversity in a single step. Does this mechanism make sense for this sequence? As you notice, we're now putting together the two different mechanisms that we've seen into a single reaction sequence. Does this make sense to everyone? Any questions on this example? Perfect. So this is a good stopping point for today. Any last minute questions before we archive today's recording? So what we'll do is we'll archive today's recording, and I really appreciate everyone being here today. I know it's the first session after spring break, and I'm glad to see everyone here and participating.